Dear students, in this lecture we will talk about the Great Orthogonality Theorem. This is the one of the important theorem in symmetry and group theory. So in this theory we have five postulates. So we will do one by one what these postulates are and what this Great Orthogonality Theorem tells us. So first important rule for the Great Orthogonality Theorem is the sum of the square of the dimensions of the irreducible representation of a group is equal to the order of the group. In that way, so we have n number of representations. So sum of the square of the representation that is equal to the order of the group, that is your H. So let us take example. So this is the character table, and as you know that these are the dimensions of any character table. So for this C2V character table, all the representations are one dimension representations. We have A and B representation. So according to the first postulate of Great Orthogonality Theorem, the sum of the square of the dimensions of any group is equal to the order of the group. So for example, this C2B, so 1 square plus 1 square plus 1 square plus 1 square, that is equal to the order of the group. So that answer comes up 4. It means the order of the group is 4. And also we know that the number of symmetry elements in this group is 4. So order of the group is already, we know that it is 4. But the sum of the square of the representation that also come up as 4. So our first postulate, the sum of the square of the dimensions of the irreducible representation that is equal to the order of the group. Next is the second postulate of Great Orthogonality Theorem is the sum of the square of the characters of any irreducible representation is also equal to the order of the group, that is H. So how that is? So for example, this is one representation, and the sum of the character, these are, we all know these are the characters of any group. So if I multiply like 1, it's number 1, uh, because if nothing is mentioned, it means it is 1. So all the symmetry operation there are count as 1. So that's why I put it as 1 into 1 square plus 1 into 1 square plus 1 into 1 square plus 1 into 1 square. So that is again come up as 4. In the same way, if I take the example of A2 representation, again 1 into 1 square plus 1 into 1 square plus 1 into minus 1 square, again it is positive 1, 1 into minus 1 square, and again it's equal to 4, that is your output of the group. In the same way, you can take any of the example like P2, again it will be 1 into 1 square plus 1 into minus 1 square plus 1 into minus 1 square plus 1 into 1 square. Again it is equal to 4. So that means that any of the sum of the characters of any representation, if I take the square of them, then it is equal to the order of the group. So it is not true for only for C to V point group, it is true for all the point groups. Next is the third postulate, the vectors whose components are character of two different irreducible representations are orthogonal. Orthogonal means if this we multiply them, then the answer should be 0. So how we will verify this rule? So I just again I am taking the example of C to V. So if I want to know whether the A1 and A2 representation they are orthogonal to each other or not, so what I will do, I will take the sum of the representations, multiply these two representations and take the sum. So it will be 1 into 1 into 1 plus 1 into 1 into 1 plus 1 into 1 into minus 1 plus 1 into 1 into minus 1. So what will be the answer? These two are negative, these two are positive. If I sum them, 2 minus 2, that is equal to 0. Again, if I want to check whether A2 and B1, whether these two representation are orthogonal to each other, what I will do, I will take 1 into 1 into 1 plus 1 into 1 into minus 1 plus 1 into minus 1 into 1 plus 1 into minus 1 into minus 1. So this will be plus 1. This is minus 1. This is minus 1. This is plus 1. Again, my answer is 2 minus 2. That is again 0. So any of the two representation in any group, they are orthogonal to each other. Means if I take the multiplication in this way, so that comes up at 0. The fourth postulate of this great orthogonality theorem is, in a given representation, whether it's a reducible or it's a irreducible representation, the characters of all the matrices belonging to the operation in the same class are equal. Okay. It means any of the representation, if they are belonging to the same class, then it is equal to, they are same. The operations that are belonging to the same class, the character of all of the matrices will be equal, will be identical. So I cannot take the example of this point group. Rather, I can take the example of C3V character table. So in this case, we have three different classes. Although symmetry operation order is 3 plus 2 plus 1, order is 6, but we have three classes. So what are the classes? We have identity, we have C3, we have sigma V. So you know there are three sigma V. So under one representation, if it is one for one particular plane, for other two particular plane, the character will be identical. It will be one only. For example, for this particular representation, if one vertical plane is minus 1, the other two will be also be the minus 1. It means the characters that we're getting over here. So although we have three symmetry operation under this one class, so all the characters that come under the same class of that symmetry, that will be identical in nature. Last postulate is, the number of irreducible representation of a group is equal to the number of classes in a group. Okay, so what does that mean? So in this case, how many classes are there? 1, 2, 3, 4. We have 4 classes. So I should have 4 representations. Okay, so A1, A2, B1, B2. We have 4 representation, irreducible representations. So the number of the classes in a group is equal to the number of representation in that group. So in the same way, you can see the example of C3V. So you can see we have 3 representations, 3 classes over here, and in that way we have 3 representations. So it depends how many symmetry classes are there. So accordingly, the number of representations will be same. So in that way, you can say the number of rows and number of the columns in any group will be same, because it will be like if these are 4, there will be 4 representations. If they are 6, then 6 representations will be there. So in that way, we can say that the number of number of rows and number of columns will be same in any of the group. So in the next lectures, we will talk about how these representations are useful and how we predict them. And then we will see how the reducible representations are formed and how we convert these reducible into the